Okay. So, this lecture today is sort of branching off into a side topic. So, most of the past weeks we've covered what I consider to be something absolutely vital for programming in R. You definitely need to know things like vectorized commands. You should know things like writing functions. You should know how to do a loop. You need to know dplyr, ggplot, all that to work with R the way that I think most people should learn to write with R. You don't necessarily need to learn everything you'd have today about strings and text. And in fact, many people get by without knowing it. The thing is, though, is they do not realize how miserable and painful their lives are working with these sorts of data if they do not learn the things that you will get today, particularly regular expressions, which we're going to spend a lot of time with. So, first things first, today's data that we're going to use are food safety inspections in King County from data.kingcounty.gov. I use in this class a lot of data from data.kingcounty.gov because there's just neat data sets and it covers Seattle. These data, if you want to use them, are pretty large. You want to download them to a local file. You could load them up directly from the website if you want like this, but you'd want to save them to a local file and load it from there. These data are kind of fun because they are restaurant inspection data from a city we all live in. So it's all the data on whether or not your favorite place to eat is actually secretly filthy, right? And we're going to talk a lot about that today. Okay, so the data looks something like this. We have things like the name of the restaurant or place of business. It includes coffee shops, restaurants, any place that has a permit to serve food or drinks. Inspection dates, some description of the type of restaurant. It has all the addresses, zip codes. Latitude and longitude, we're going to use these in the mapping lecture next week. And inspection scores and things like that. Types of violations when inspections were done. The thing you'll notice here is that there is a ton of text data in this data set. In fact, many administrative data sets have tons of text. Things like the name of the restaurant is text, its address is text, the city. The zip code is actually text. It looks like a number. Most of us would think of a zip code as being a number. It is a string. It is not, like this is not 98,126. It's the zip code 98126. It's text. All the stuff, for the most part, is actually sort of string data. If we want to work with these things, we need some sort of tools to know how to manipulate all this text to make it in some usable format for us to do analyses or make maps or something like that. Okay, so I've used the term string a bunch of times in this class. It refers to character data. So strings are some sequence of characters. The characters can be any type of character. They could be alphanumerics. They could be special characters, whatever. Numbers, letters, whatever. But the main thing is that there's usually a bunch of them, and they are all stuck together as one unit. In other programming languages than R, strings will often refer to just a sequence of numeric information. Like, for instance, binary strings, right? So these are single byte, 4 single byte strings. We would call this a string. It is not numeric data, it's a sequence of numeric values. In this case, it's just zeros and ones. We rarely use this type of string in R, but when it comes down to it, your computer entirely operates on strings like these, usually 8 of them at a time, zeros and ones. These are sequences of numbers rather than a single number, and that's what makes them strings. A 0 or a 1 is a single number. A 0, 1, 1, 1, 0, 0, 0, 0 is binary for P, and that is a string. Okay, so basics of strings in R. In the past, we've used the nchar function to get the number of characters in a string. If, for instance, I wanted to check to see if my zip code data in this restaurant's data set were valid, I might say, I just want to see what is the length of all the different zip codes in the data set. I could say, restaurant's data, mutate a new variable called zip length equal to the number of characters in zip code, and check it out. What we see here is that of the inspection data, roughly 260,000 of them are 5-digit zip codes like they should be. One of them has a full 10-digit zip code. Why? I don't know, but it does, right? This would be a quick way to do a data check. If you expect all of your strings of some type to be a particular length, nCharacter will get the length of those. Used it a few times in this class. Substring is something we used in the voting homework. It's been in my lectures a couple times. We could use substring to get some subset of a string and extract it from an item. In this case, maybe I just want to get the first 5 digits of the zip code. Maybe I had hundreds of zip codes that had way more characters than they should, and I only want the first 5 for all of them. I could say I want to overwrite my restaurant's data by creating a new variable in restaurants that is zip_5. It's going to be my 5-digit zip codes. I say substring, take the original zip code variable, start at the first character position, so go from the first number, say 9, it starts with a 9, and then end at the 5th position, discard everything that comes after the 5th position. And then I look at this variable, and now my zip5s are all 5 digits. Right? Substring would just grab 1 through 5. Does that make sense how substring works? Use it a couple times. Okay. Paste is another one we've used a couple times in this class. We can combine parts of strings together using paste. Commonly, we'll take 2 different columns that are character data, stick them together into one column. We use paste for that. An example here is I take the restaurant's data. I want to make a mailing address. So if we remember in the restaurant's data, the street address, the city, and the 5-digit zip code are all different columns in the data set. If I wanted to generate their actual mailing addresses, I'd have to put these all together. Maybe I want them formatted nicely like an actual mailing address. I can say, I'm going to create a new variable called mailing address. It is going to be equal to paste together the address, comma, space, the city, comma, space, Washington, space, the zip code, separator, nothing. Meaning I don't want to separate all of these different entries in here by anything. Now I have a new column, mailing address, that looks like this. It has the original address, which was 2920 Avalon Way, comma, space, city was Seattle, comma, space, Washington, space, the zip code. So I've assembled a mailing address for every one of the restaurants in my restaurant's data using paste in a mutate command. This is an example of sort of a common usage of paste. Lots of different data that all can belong together in some situation. Stick them all together with paste. Does that make sense how that works? Any more questions? Yes?
I remember previous slides we used paste 0.
Yes, paste 0. Do I have it over here? I have paste 0 in about 2 slides. Paste 0 does the exact same thing as paste with separator equals nothing. It's a shortcut. I could have used paste 0 here and gotten rid of sep equals that, but I'm kind of displaying both of them at the same time. We'll see about them a little bit more in a second. Anything else? Okay. So, paste with collapse is something I haven't shown you guys yet, at least I don't think so. What collapse does is it will take, say you give paste an entire vector of character data. Normally, paste will output a vector of the same length as the vector that comes in. What collapse does instead is it takes that entire vector and pastes all of the elements of the vector together into a single element. And it separates those things it collapses together by whatever you give in the collapse argument. Okay? Some way you might be able to use this usefully is say we want to extract from a data set the column types. Maybe we have a data set we've worked on before. We have set column types we've created in that data set, and we're going to go load in another data set with the same columns, and we want to apply our old column types to this new data set coming in. We could write a function to do that, or we could do it, or well, first we'd have to extract those data types. So if I take my restaurant's data and apply to restaurant's data the class function, it will extract the data types of it. Do people remember the apply functions we used in the previous week? Apply says, okay, take some data set, some item here, and to every element of that item, run this function on each element individually. This is a data frame. An element of a data frame is a column. So if I run sapply restaurants class, it runs the class function on every column of this data frame. So it will return the output of every column type as one big vector. Okay? If I say get the class, the output of this, so it's going to be things like, the output will be like numeric, numeric, character. It'll be those whole words spelled out for each individual one of the columns. I could get substring the column types 1 to 1. This will get the very first letter of each one of those column types that came out of that function. For instance, for the word character, it would just extract the letter C. For the word numeric, it would extract the letter N. I could then say, okay, all those column types are in this big vector. So one element is C, one element is C, another element is N, another element might be capital D for date. I want to paste all of those together, but I want to collapse them. Collapse means that that vector has as many elements as there are columns in our data set. Collapse says I want that to be one element, all those letters jammed together. The output is going to look something like this. C, 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 N, N, C, C, I, so on and so forth. This is because these columns were character, 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 numeric, numeric, integer, date, and so on. I've pasted them all together. If we remember way back to our reader lecture, the column types argument to like read underscore CSV or read underscore TSV takes an argument that looks exactly like this. That's because it's designed so that you can use this sort of thing to extract the column types from a data set and apply them to another similar data set just by directly collapsing them and inputting them into that read underscore CSV. This is a thing most of you guys will not need to do, but if you do want to know how to do it, you can steal my code and use it, because otherwise it might be troublesome and you might not remember you can do such a thing. You could even make a function to do this for you. So if you're reading in data using read underscore CSV and you want to use the column types, right, you could write a function that works like this. It's some function that takes a data frame, you give it to as an argument, it will return the column types of it. So I might do reader input types, give it the Swiss data set, and it pops out and says, oh, numeric, numeric, integer, integer, numeric, numeric. I can grab those column types. I can do it with the restaurant's data, it outputs this. This would allow you to read and then apply them, say, to a read underscore CSV if you want. Okay. So some applications of paste and collapse. So paste 0, like you asked about, paste 0 is a shortcut for paste that has no separator. That is, separate equals nothing. By default, paste works like this. Let's say I give paste 2 different vectors. I'm giving it the number 1 through 5, the numbers 1 through 5, and the first 5 lowercase letters of the English alphabet. By default, the separator is a space. So if I paste these together, it's 1 space A, 2 space B, 3 space C, so on and so forth. If I instead say paste separator equals nothing, it sticks them together, there's no space there. That is identical to saying paste 0. It just sticks them together. Paste 0 is just a lazy way of writing this exact same thing to save you from typing comma sep equals nothing. Does it make sense? People familiar with these paste functions? Okay. So, separator controls what controls what happens when you do entry-wise squishing of vectors together, right? Collapse controls how they go from being a vector into a single string or a single element. These are some examples of different things that would happen given different arguments to collapse and separate for different vectors here. You might want to, I would recommend that you look at these and understand what is happening in each one of these function calls, right? So this is a basic one here. I'm saying paste letters 1 through 5 and collapse. So this is the first 5 letters. I'm saying collapse by exclamation point. Because I'm using collapse, the output is going to be a single element. It's not going to be multiple elements. And what divides the individual elements that were in this vector is the exclamation point I gave for collapse. Does that make sense? Okay. Another one might be, I do paste the numbers 1 through 5, first 5 letters, separate equals plus. This is going to be 5 elements, because I used separate without using collapse. And the thing that separates each one of these pairs of elements is the plus. I might do a collapse with question marks. It looks like this. Notice here that I'm doing the numbers 1 through 5, letters 1 through 5, and collapse question mark. Look at how it collapses together. it first pastes together the first element of each of these vectors, that is 1 and the letter A, pastes them together, then it does 3 question marks, then 2B, question marks, 3C, question marks, 4D. It does the pasting, then it does the collapsing. Okay? I could also give something like the numbers 1 through 5 and then a single letter. Remember, in R, it will do vector recycling to make sure that this Z is the same length as this, so it's going to basically replicate Z 5 times. So we can imagine we're pasting the numbers 1 through 5 to just 5 Z's in a row. I do a separator star, I get 1Z, 2Z, 3Z, 4Z, 5Z. Okay? Then lastly, I'm pasting together the numbers 1 through 5, Z again, separator, and collapse. So the first thing it's going to do is it's going to paste them together with the separator. Then it's going to collapse each individual of those entries with space, tilde, something, and you get something like that. So you can mix and match these. Sometimes you'll have some idea for what you want text to look like. Maybe you want to iterate over 1,000 different regression models in some data science project, and you want to generate all of the formulae to make all those models in some big loop. You could do it this way using combinations of paste and collapse and the right separators. You'll probably not need to do that, but if you do, that's how you do. Do we have any questions about that? Yes?
Instead of getting 1 plus A, 2 plus B, what if I want 1, 2, 3, 4, 5, and A, B, C, D?
Ah, yeah. You'll want to do a mix and a match of different things. So, you could, for instance, have something that generates, say, the numbers 1, 2, 3, pastes those together, collapses them, and then pastes together like A, B, C, and then sticks those together. So you probably do multiple commands. If you think about it hard, there might be a way to do it in a single paste command, but nothing comes to mind. I'd have to toy with it. But you just kind of mix and match. It's usually easiest to do multiple calls to get the individual components you want, then stick them all together. Any other questions?
On
Yeah.
the third line, is that a typo or is that 0 supposed to be there?
That is supposed to be there.
Okay, so what is that?
Paste 0? That's just separator equals nothing. So this paste 0 call right here is making these two, so the number 1 and the letter A is the first element of this, it's making them paste together with no separator before collapsing them. Yeah. Yeah, me being sneaky.
Yeah, I see that.
Okay. Okay, so we've learned a little bit about using certain base R string manipulation stuff. We're now going to discard a lot of that and use functions built into the tidyverse instead, because they are way more powerful. So stringr is yet another R package from the tidyverse. Things like ggplot, dplyr, tidyr, lubridate, reader, almost all the packages I use in this class are from the tidyverse. Stringr provides a huge range of really useful functions for doing important stuff with strings in a very user-friendly way. It replaces some functions like paste and endCharacter in ways that are a little what I call less touchy. In other words, they just work better with missing values and they work better with factors. I still use the base paste and paste 0 and endCharacter most of the time, but if I have problems with missing values, I'll use the stringr versions. But it adds functions that don't exist in base R or are hard to use in base R to do more complicated things, like removing whitespace or padding whitespace out. That is, removing extra spaces on the outsides of strings and things like that. Or adding like additional zeros or removing zeros from things. And most importantly, stringr adds functions to do tasks related to pattern matching. That is detecting, locating, extracting, matching, replacing, and splitting text based on some sort of logical pattern. In other words, they use a language of searching through text to accomplish tasks for you. The language that stringr uses, and also every computer application in existence uses for doing text searching at some level, is something called regular expressions. Regular expressions is a language for logical selection of text that is universal across all computers and across all operating systems. It's been standardized since the 70s. Every operating system, every language uses it. You may or may not have encountered it, depending on how much coding you do and how much you like actual text searching on computers. But regex exists everywhere. If you don't know how to use regular expressions, you're putting yourself at a massive disadvantage in working with data. So I'm going to force you to learn them, at least a little bit today. It's kind of a bottom as well. So for some of these operations, there are base R or stringy versions for these, but they're a lot harder to use. Stringy is a package most of you will never ever encounter. It is the package that underlies stringr and does most of the actual text operations for tidyverse packages. You don't actually see it. It's really hard to use directly, but it's tremendously powerful. One convenient thing about stringr, much like the forcats package I talked about in a previous week, is that just about all the functions in stringr begin with str_, so it makes it easy to find them. In your autocomplete in RStudio, you can start typing str_ and then bring open your autocomplete and hunt for that function you forgot the name of. I love it when packages do this, and it's great. So, the library is just stringr. If you've installed tidyverse, you have it. Okay, so there's some equivalencies, stringr equivalencies to base R functions that we've introduced that are useful in their own way. String_sub is like substring in base R, but it allows negative indexing. So negative indexing means we can do something like this. Let's say I have some character data I want here, but I want everything except the last two letters of that string. I can say string sub Washington, start at the first letter, and go to the negative third letter. That is, count 3 letters from the end of that back in and give me up to that. So -3 means it's going to cut off the second from the last and the last letter from it. So if I do Washington 1 -3, I get Washington. String sub. Okay? Negative indexing is really useful because often we want to just chop stuff off the end, right? Often you'll have variable names that are like variable name _ a year. You could just chop off that underscore and the year and get the variable names you want out of it. Okay. String _c, string combine, works basically just like paste 0. It's paste where the default is blank, but it can still take a separator argument. I still use paste 0 most of the time because I remember paste 0, but string c might be good to use that. Nothing fancy there. Instead of n character in stringr, you could use string _length, returns the exact same thing as n character. I think it handles NAs better, but that's about it. Okay. There's some handy functions in stringr that also exist in base R, but are easier to remember in stringr for doing case changing. Very often, you'll have string data, lots and lots of text data, say names of restaurants, names of countries, names of cities, that have irregular case to them. Maybe they have mixed capitals and lowercase. Some are all caps, some are all lowercase. Some are camel case, some are sentence case, whatever, right? The functions string to upper, string to lower, and string to title will convert the case of individual characters in strings to whatever you want. This is something you want to do before data cleaning very often, right? So if I look at the unique cities in my restaurant data, some of them have Seattle in all caps, some have it in title case, and whatever, right? These are not different things, it just so happens the case is different. To R, these are completely different, and so it won't group them together automatically. So before doing any kind of data cleaning on this, I'm just going to go ahead and convert all of them to uppercase. To do that, I would say, take my restaurant's data, and here I'm going to say mutate at var's name, address, and city. Do you remember what mutate at does? Mutate at is a way of doing multiple mutate commands at the same time. So if I want to do the exact same thing, in this case I want to convert a bunch of different columns to uppercase, I can say I want to convert name, address, and city all to uppercase. So the variables I want to mutate are name, address, and city. The function that I want to perform on name, address, and city is string to upper. This is me basically applying a function to 3 different variables at the same time in dplyr. If I do that, now it will have converted name, address, and city columns all to uppercase. So if I get unique on the city column in my data set, you'll see I no longer have a lowercase Seattle, I just have all uppercase, Kent, Bellevue, Kenmore, Issaquah, Burien. I don't have lowercase Issaquah, lowercase Seattle. I've converted them all to uppercase. when I'm working with text data and data sets and the capitals don't have an important meaning, I will usually convert the entire data set to either uppercase or lowercase right away, just so I don't have to deal with it later. Yeah.
So in this way, you actually replace the original data rather than
Yep.
create a new variable.
Yeah, in this this particular like slide, I'm actually just overwriting restaurants every single time I'm doing anything. I'm just replacing everything. It's because the way that these data were originally done to do these manipulations before I wrote these slides with the restaurant data, every command in the slide was actually done in one dplyr chain. So I just had one assignment at the top, and I just loaded the data, did all the processing all the way to the end of it in one chain, and then I broke it up for the slides. And to do that, I just overwrite everything. I normally don't create any objects if I can help it when I'm doing R code, and we'll see that probably in the new lecture I'm putting together for week 11, where I'll do kind of advanced data manipulation, show how I'll do an entire project on one dplyr chain. No. Any other questions? Okay. Another useful function, string trim. So it's very common in text data, especially administrative data, which is always the bane of my existence, that you will get random errant spaces, right? You'll get something like this. The name of this restaurant is at the Shack LLC, and then there's just a space at the end. Or maybe it will begin with a space. Maybe it will end with 10 spaces, like my police data always seem to do. They'll end with like 10, 20, 100 spaces for no reason. Actually, there is a reason. It's because it was originally punch card format data. But still, lots and lots of spaces. String trim is a way to get rid of these errant spaces in your data. Works like this. First of all, any character column in my entire data set could potentially have these white spaces. So I'm just going to say I want to trim the white space off of every text column in my entire data set. I'm going to do it like this. I'm going to say replace the restaurants data, restaurants, mutate if. So in the last slide I used mutate at. Mutate if also lets you do some mutate command on multiple columns in data set, but instead of selecting the particular columns directly, you give some sort of function that returns a true or false on each column. If it returns a true, it will do the operation you tell it to. Okay? This is character. So what it's going to do is it's going to go down every column in the data set. Anytime it encounters a column that is character data, it's going to do string trim to it and trim the white space. If it encounters a numeric column, it will do nothing. This is another way of doing many different mutate operations on something without writing a whole bunch of text. I try and write as little text as possible. So what this did is it ran through my whole data set. There are a lot of different character columns. I mean, there's like a dozen character columns in the data. It string trims all of them. What does that output look like? I do head unique restaurant's name. Remember before? At the Shack LLC has a space here. The space is gone. In fact, any additional spaces at the beginning or end of that text are gone. String trim does not remove the text inside because it assumes that's meaningful text, but it removes any extra spaces at the beginning or end of things, which are really common in like real-world data sets. People just have extra spaces stuck in there for whatever reason. Does that make sense? It's pretty easy. Being able to do things like mutate if with is character or mutate at will save you a lot of time writing code, though, so figure out how to do that stuff. I don't think I require you to do any of that, but it's nice to know how. Okay, so those are sort of basic functions. Now we're going to get into what will probably look like some really crazy stuff with dealing with text, but I promise you it's really useful and really powerful, and we're going to work through a lot of examples together to try and make sense of it. Okay, so regular expressions, which are often abbreviated as regexes or regex, are the way that you describe to a computer how you want to get some text. It's essentially, it's the type of text you'd say to the computer. Essentially, you're Googling for things. You're doing a search on some text. But you have to be very specific about how or what that text looks like, because computers want things, very cut and dry. You can't be vague about it. So you need some logical language to communicate exactly what you want to the computer so it can spit it out for you. The way regexes work is you will write some sort of expression, and those expressions are essentially like expressions we've written for like filter commands in dplyr. It's some logical statement. It will return whatever gets a true and ignore everything else. So we'll write an expression that will be applied to a string, and then we can do something with all the matches that it has, essentially all the trues that expression returns. There are two components to regular expressions. There are literal characters. Literal characters are the snippets you want to search for of actual text. Maybe I want to find the text SEA, like we did in our homework. I used substring for that in the key, but we could use regular expressions to do it better. Or say the number 206, like a phone area code. Everything else in a regular expression is what is referred to as a meta character. Meta characters are things that let us be flexible in the way that we're specifying some pattern for the computer to find. All of these symbols, backslash, caret, $, period, pipe, question mark, asterisk, so on and so forth, are meta characters. Meta characters will do something special. We're going to walk through a few of these different meta characters, but there's an endless wealth of them. If you want to learn all the meta characters in regular expressions, save yourself a weekend to do that. If you want to treat a meta character as a literal character, that is, if I actually want to search for a parenthesis, in R, we have to put 2 backslashes in front of that meta character to escape it. That's the terminology. You escape a character with backslashes. So if I wanted to search for parenthesis 206 parenthesis, including those parentheses, I would have to search for it like this. Backslash, backslash, parenthesis 206, backslash, backslash, close parenthesis. This is me telling R, or telling more specifically the Perl engine that runs regexes, that I actually want to search for a parenthesis. I don't want to use the parenthesis as a meta character, because parentheses group things in regular expressions. So just keep this in mind. We're going to see a lot of backslashes being spammed all over the place in a minute. Okay, don't need to memorize all this. It's complex. We're going to get working examples. Okay, so a function you want to use with regexes is string detect. String detect is a function I use all the time. It's for detecting some pattern in string data. So let's say in these restaurants data, I want to look at health inspections for coffee shops. I'm going to assume that something in our restaurant data is a coffee shop if it contains in its name the text coffee, espresso, or roaster. The regex for coffee or espresso or roaster is just coffee, bar, espresso, bar, roaster. If you remember when we were searching or doing like filter commands, bar stands for or. It does here too. If I wanted to search for all that text in the names of restaurants, I could use string detect. String detect returns a true when it finds any of the text in that pattern. If it does not find any of the text in that pattern, it returns a false, meaning we could use it in a filter command. So here I'm saying restaurants data, pipe it into filter. Then I'm saying string detect, look inside the name column of the data set for coffee or espresso or roaster. And then I spit them out. What do we get? Two Sisters Espresso, 701 Coffee, 909 Coffee and Wine, AJ's Espresso, so on. Right? These contain one of the things I asked for each. They could contain multiple, so still returning. This is using a string to search for stuff in other strings. It's pretty powerful. Any questions about that? I'm going to get crazier with this stuff here in a second. Okay, so maybe what I want to know is if my coffee place of choice is going to kill me because it is filthy. So what I'm going to do here is I'm going to take each unique business identifier in the data set. I'm going to keep its most recent inspection score, and I'm going to do a histogram of it. This is kind of the way I more often will do simple analysis techniques in my own scripts. You'll see I start with the raw data, the coffee I created before, and I do all of my modification and pipe it straight into a ggplot command. You don't necessarily have to follow this too closely, but this is what the inspection data looks like for Seattle coffee shops. Now, inspection scores in Seattle, you get points by getting health violations. Every point is a health violation. So somewhere in Seattle are multiple coffee shops in this data set that have 40 or more health violations. It's a coffee shop. How do you get 40 health violations when you serve coffee and maybe bagels or pastries? Anyway, these are the places likely to kill me, and I might want to figure out where they are. Next week with mapping, you'll actually be able to figure out where the places that kill you are, with the homework anyway. Yeah. Okay, so maybe we want to do something different. Maybe what we want to do is search through all the phone numbers and figure out which ones are in the 206 area code. Okay? We can use string detect for this too. The thing is, though, is that some of the phone numbers have parentheses around 206. Some of them do not have parentheses around 206, and we want to get them in either case, but we do not want to get a phone number that, say, 206 is like in its place over here. We only want the ones that begin with either 206 or 206 in parentheses. Well, this is something that regular expressions are made for. I'm going to write a pattern that looks like this. Caret, backslash, backslash, parenthesis, question mark, 206. What does that gibberish do? The first thing is a caret. The caret is a meta character. It means look at the beginning of a string. So whatever search I do, it's all going to have to occur at the beginning of the string it's looking in. Then I say backslash, backslash, parenthesis, question mark. This says I want to look for a left parenthesis, backslash, backslash, parenthesis, a parenthesis, but the question mark says it's optional. If there's a parenthesis there, cool. If there's not a parenthesis there, I'm okay with it. Then, after that parenthesis, or after the beginning of the text, either way, I'm looking for 206, the literal numbers. Anything that does not fulfill these conditions will return a false. Anything that does returns a true. So if I look at the test examples I did, 206, 1, 2, 3, 4, 5, 6, 7, that should be a true. It returns a true. 206 in parentheses returns a true. 206 parentheses space returns a true. But 555, 206, 1234 does not. This is the power of regular expressions here. I had a very specific thing I wanted, but I needed it to be flexible. Using anything other than regular expressions, it would have been very challenging to isolate these 206s with or without parentheses, but not the one in the middle of the text. Anyone have questions about how that worked? The most useful meta characters in regular expressions, I think for most people working in R, are probably caret. Caret means the beginning of it, and $, which is the end of a string. So $, will let you search from the end. Caret lets you search from the start of some text. I think I've got an example of $, but I'm not positive. Okay. So stringr built into it has a function called string or str_view that opens up a viewer panel, like the view command in R, that will show you what text your particular regular expression has highlighted inside of a data set. So I could do something like string view, the phone test examples in that area code 206 pattern that I generated on the previous slide, and it would pop up and it would show highlighted in yellow what parts of the strings my regular expression highlights. Okay? It generates just a little web page in a viewer panel. Be real careful, though, with string view. Do not load like an entire really long vector or variable. It may lock up your RStudio because it has to render a web page. So if you give it something like 10 million characters long, it's going to try and generate a little web page 10 million elements long and then highlight text in it. It will crash your computer. So be judicious with the use of this. There's linked off of the course website is a regular expression testing website. That's a sort of what you see is what you get regular expression input thing. That's a good place to test and see if your regular expressions are getting what you want. Sometimes if you're working with real text data, complex text data in R, you're going to be doing some really complicated matching and searching, so it's kind of nice to get live feedback while you do it. Okay, so maybe we want to know how many rows in the data set have non-206 numbers, 206 being the dominant area code in Seattle. I could say I'm going to mutate a variable, has 206 numbers equal to string detect, the phone number, area code 206 pattern I created on the previous slide, and then I'm just going to group by whether it has a 206 number or not and tally. This is essentially group by and tally is the same as me saying count has 206 number. It creates a frequency table. So false. So false are numbers that do not have a 206 area code. True are numbers that do have a 206 area code, and NA are ones that the expression failed because there was no phone number included. So, quick tally. Maybe you want to do an operation like that in your own work? Steal my code. Okay. We could also extract patterns. So maybe we don't want to return trues and falses. Maybe we want to actually pull out the text that we match. To do that, we can use str_extract, string extract. Something we might want to do is we might want to extract the directional part of a Seattle address. If you've lived in Seattle a while or have just paid attention, you'll note that all the addresses in Seattle, except in the center city, contain some letter like north, northwest, southeast, something like that. If somebody gives you an address in Seattle or a pair of streets and gives you, say, northwest, you should be able to know exactly where it is in Seattle because Seattle is set up on a like 8 category. You'd think it'd be 9, but it's actually I think 8 grid where every address that's the northwest is in one particular square of the city. Every address that's south is in one particular area of the city, so on. Anyway, we might want to extract that because that's meaningful information. To extract the directions, I'm going to use a pattern that looks like this. It's a little bigger than the previous one. Space, parenthesis, all the different possible directionals separated by bars, close parenthesis, a new parenthesis, space, or $, close parenthesis. Then I have some example addresses where, for instance, I want to extract W here, northwest here, nothing here, and nothing here. Okay? So if I run this string extract on it, I get the west, I get the northwest, and NA, NA. What is this doing? So the first space right here will match a space. It will go through the text, it will hunt for a space. Okay? Then, after a space, it's going to match one of these things. North, northwest, northeast, south, southwest, southeast, west, or east. Just one of them, but at least one of them. Then, this group over here says, okay, there could be a space after it. For instance, this could be northwest space 65th Street, or not. The not is a $sign. The $sign says it's also okay if instead of that W is followed by a space, it could be followed by the end of the string. Okay? The reason I'm doing this is because I don't want to say get N and then have the D right afterwards. If I don't say space or end of string, it could hunt through, find that N and try and grab it because it's in the middle of a word. This says it needs to either have a space after it or the end of the string. Okay? So I get what I want. I get my directionals, W, northwest, NA, NA. Because I've said I want the space, or I'm selecting the space, it also returns the space. Okay? Does that make sense? Any questions about this? Okay, maybe I want to find where all the different addresses, all these different restaurants are in the city. I could say, okay, let's get the distinct addresses, because this is actually a panel data set. Each restaurant gets inspected multiple times. So I only want each restaurant once. So I get its address. I say the city region is equal to the string extract I did before, but I'm string trimming. I introduced string trim earlier. It's to get rid of this extraneous white space like this on my directionals. Okay? I do that. Then I just count the city region and arrange them. In my data set, I see most of the restaurants in the data set are in Northeast Seattle, followed by South Seattle, followed by Central Seattle. NA means it failed to find a match. The only ones that don't have a directional are the ones in the center of Seattle. North, southeast, southwest, east, northwest, and west. Okay, so there are 9. Okay, does that make sense? I've extracted some text data. I've done something useful with it. Cool. Okay. String_replace is kind of like extract, but instead of extracting and pulling out the strings it makes a match with, it replaces them with something else. It deletes them and fills in new stuff. You could use it to just delete, but you could also use it to delete and then replace. So maybe we want to do something like a street-level analysis of the inspections. Maybe I want to see what street in Seattle is filthiest. Is it going to be the Ave? Is it going to be Pike Street? Is it going to be, I don't know, James Street or something like that? How could we remove the building numbers? So in our addresses, we have things like 2812 Thorndike Avenue, 1st Avenue, 10A 1st Avenue, 5201-B University Way. I have addresses like this. I just want University Way Northeast. So I have to get rid of all of this junk. And in Seattle, you get addresses like this. 7040 and a half 15th Avenue. We need to capture all of that and get rid of it. Okay? So I'm going to use a pattern that looks kind of hideous. I'm saying caret brackets 0 through 9, star dash question mark brackets A through Z question mark space, and then in parentheses 1/2 space question mark. You're like, what the hell is that? It's actually really easy. Let's break it down. So this begins with caret, then 0 through 9. This says, okay, I want to start at the beginning of any given address. Then I want to look for any number between 0 and 9. This is how you search for any number in a string. So 0 through 9, the star, so 0 through 9 star means match as many digits as you want. So it could be the number 9. It could be the number like 55,768,545. Doesn't matter. It's going to match all of those numbers put together because I put an asterisk there. You could also specify a specific number of them using a different meta character, but I don't remember it offhand. Okay? So, in an address like 2812 Thorndike Ave, we now know how to match 2812 because it's just 4 numbers in a row. Okay? Next, dash question mark means optionally match a hyphen. It's okay if the hyphen is not there, but if a hyphen is there, we want to match it too. Then A through Z in brackets means, with a question mark, means optionally match any letter A through Z. It doesn't have to be there, but if there is a letter, I want that. That's how we're going to get something like 5201-B. We've matched the dash, and then we can match any single letter. If it's actually 2 letters, well, we're screwed, and I'll have to adjust my regular expression. But that'll get a single letter. Next, I'm going to match a space. So the address could be something like 5201-B. It's probably going to be followed by a space. Okay? Then, optionally, I'm going to match a 1/2 followed by a space because people in Seattle like to do these 1/2 addresses. It's because they actually built on a single plot and then divided it up into 2, and they didn't have enough addresses on a block because sprawl, I don't know. Okay, so anyone have questions about all that matching? You can see it can get kind of crazy, but if you just think about it component by component, you just keep putting them together until you get what you want. And you can play with it until you get what you want. I didn't just like know immediately when I was writing this, oh, well, obviously it's going to be caret brackets 09 star dash question mark. You know, no, I added these bit by bit by bit. And I'm like, okay, now it does what I wanted to do. Right? It's iterative.
With the asterisk, if you had more than one letter, if you put it after a letter chain, would
Yep.
it be the same thing?
It would get more than one letter. Yeah. I just didn't think it was necessary. It could be. Yeah. Cool. So, maybe we then want to remove those street numbers to just get the individual streets. I could take the restaurant's data again. I'm going to create a new variable called street only. So that's going to be just the streets, not the full street addresses for each restaurant. I'm going to do that by saying string replace. So we're going to take the address variable. I'm going to match that address number pattern, and then I'm going to replace it with nothing. So string replace in this case, I'm using it to delete all the text that matches it. So if I delete all of the actual address numbers, the thing that is left is the street itself. So I get things like this. Southwest Avalon Way, Mercer Street, Fairview Avenue North, Unit 1700A. I'd look at that and be like, oh God, I gotta get rid of that stuff too. First Avenue, East Valley Highway, so on. So I've deleted the actual like front part of that address. I've left behind some unit type information though. So maybe I want to get rid of the units and suite numbers at the back. So there's a lot of variety to the unit and suite like reference numbers at the end of these addresses, but a sort of first shot at it might be to drop anything at the end of a string that includes and begins with pound, STE, suite, shop, or unit. Those are the ones I found on a cursory search. Yeah, so maybe I want to get rid of those and anything that occurs after them. Okay? As long as it's, yeah, anything that occurs after them, actually. So this unit pattern is going to be space, and then in parentheses, pound, suite, or, pound, suite, or shop, or unit, period, asterisk, $. So I'll run through what that does in a minute. So test addresses are going to be things like, okay, I want to remove Rainier Avenue South, number A. How do you have a number A? Anyway. Rainier Avenue South, number A is going to return Rainier Avenue South. Fauntleroy Way Southwest, Suite 108 will return just the street. Number 100C returns just 4th Avenue, and so on. They look like they work, but they're also not cutting off useful like street information and things. So, how's that regex work? This one says, first we're going to match a space, because all of these ones are going to be like some street name space unit blah, right? Then I'm going to say, okay, I want to match one of these words. I want to match a pound, a suite, shop, or unit. Any one of them will do. Then I say period asterisk. Period in regular expressions says match any character, anything at all. Period star means match any character repeated any number of times, right? And then the dollar sign is the end of the string. So what this is saying is match pound, suite, shop, or unit, and then match anything that occurs after that all the way to the end of the string, no matter what it is. This is me just saying, okay, if it has suite in the name, I'm just deleting everything after that, right? Okay. Luckily, this doesn't have business names, because you could have business names that are named like, oh, Suite 608. Yeah, you don't want to use that on the names, but it works with the addresses. Okay. And it works, for the most part. So if I say the street only is going to be string trim, string replace, street only, address unit replacement, replacement that, I'm like getting rid of all of that content. I get things like Southwest Avalon Way, Mercer Street, whatever, but then every once in a while you'll see something like Northwest Gilman BLC-08. That's one of those cases where I'm like, I don't know what the hell that is. I'd have to probably Google Maps this, figure out if that C08 is actually part of something useful. Maybe it's a service road. Who knows, right? Okay. So, if I want to get rid of that, I have to program into my regular expression too. Okay. So, now that we've stripped down to the actual street addresses, I may want to know where food danger lurks in Seattle, okay? So, what I want to get is one row per restaurant, per date of inspection, with the score for that particular restaurant, and I want to see which streets have the most restaurants with scores above 45. That is 45 health violations in a single inspection. So I say, restaurants data, go to distinct business IDs, distinct dates, inspection scores, and distinct streets, individual streets. Filter to inspection score is greater than 45, then count the streets. Arrange by descending, get the first 5. Unsurprisingly, there are 108 restaurants, University Way Northeast, with inspection scores 45 plus. We all eat on the Ave, it will kill all of us, okay? South Jackson Street, International District, it will poison us. Pacific Highway South, so this is like Aurora, it will kill us. Northeast 24th Street is like Southeast Seattle. Rainier also, they will kill us too. So, if you want to know where to find food that is bad for you, and also delicious, it's going to be all of these places, right? Okay. So, regular expressions let us get useful stuff. We extracted a lot of cool information out of this with these really complex, weird addresses, right? The only way we could possibly get down to the individual addresses for all of these is by using regular expressions, unless you want to do it manually for every single one of the addresses, right? Regular expressions are really powerful and really important to learn because you can do cool things with text. And most of us at some point are going to be working with real text data to do things like this. I mean, maybe you're not going to spend a huge amount of time trying to figure out whether or not your food will poison you because you can just see whether other people have gone there and survived. But, you know, maybe you want to do this. On the, I think I don't have it in this particular slide anymore, but I discovered that the filthiest single restaurant location or food service location in the entire city of Seattle is in a fraternity right over there. It had like over 100 health violations in a single inspection. I was like, what is even left to not violate? If you have that, I mean, it's like, how many points can you violate? It was amazing. Anyway, so fun facts. Yeah.
Can you do any kind of like mapping plots with like the latitude, longitude, like geocoding, and do like a map of the poorly?
That's what the optional homework is. It's actually mapping this restaurant data. So next week's lecture, which I'm almost done putting together, Because Google changed their API on me, it basically invalidated half of that lecture that I originally had written. So I've rewritten the lecture for like mapping and geospatial data analysis, completely rewritten it for this term. And it's actually focusing on geographical data manipulation. I map the elections data, I map all that other stuff, and we'll see how to work with that stuff. Next week, the homework is still using these restaurant data to plot using the latitude and longitude and do some cool operations. It's an optional homework, it's extra credit, I will grade it, but don't have to do it. But yeah, you absolutely could. Could rip those data out and do it. Okay, so another thing we might want to do is we might want to just split up string data. Maybe you have one particular column that contains essentially two very different things in one text column. We just want to divide them up. This is really easy if there's some sort of divider that we know that separates, say, in this case, a health code violation number with the actual health code violation. String split works like separate does in tidier. It will, if you give it a pattern, it will divide text up into two columns based on some pattern. So in this case, I know that the restaurant inspection data works with a number violation, space, dash, space, then the text of that violation. Maybe I only care about the violation text. I could say, I want to get head of string split fixed will generate a matrix of the output. This will only work if everything you're splitting has the exact same number of separations. In this case, I know they're all just one separator between this number and this text. If you had a variety of different lengths, you'd have to go to a list because each element would be a different length. Anyway, string split fixed. I'm going to split restaurants violation description. I'm saying, okay, I want to get two columns. The first column is everything that occurs before space dash space, and the other column is everything that occurs after it. And I want to split it into two components. I get this. I get a bunch of violation numbers, and then I get the actual text of the violations as a second column in a matrix. So for instance, I get things like proper shell stock ID, wild mushroom ID, parasite destruction procedures for fish. This means that this particular place violated whatever these things are. So this restaurant did not properly identify its shellfish. It has some problems with wild mushroom IDs, and they do not follow parasite destruction procedures for fish. If you really want to know that stuff, delve into it. It's good to look at places and avoid the places that have problems with like proper cold housing temperatures. You don't want to eat at the places that aren't like properly refrigerating food, right? Okay. So if you really delve into it, yeah. It's nice that I looked at like my favorite restaurant in the world, the one next to my house, and it has no health violations anywhere in the data. Every inspection is just perfect. I'm like, yes. Yeah. Be careful looking up restaurants you actually like. Okay. Zouave, the one next to my house, little Italian place. Abe's place is awesome. Okay. Yeah. Okay. Some other useful stringer functions you might want to use. String pad is the opposite of string trim. String pad, you give it some string, some width that you want every string in that column to be, and then you tell it what side to add characters to, and then what to add. So for instance, maybe you have zip codes. You want every zip code to be a 5-digit zip code, but it's cut off all the zeros on the zip codes that begin with 0, because there's East Coast zip codes that begin with 0. You could say, okay, string pad, zip code, width 5, side left, pad 0. That will add those zeros back onto the left side of those zip codes. This is something you commonly want to do with certain types of IDs, maybe geospatial IDs. You have some geo ID from census tracts or something. You got to add all those zeros back on, pad all the zeros on. Another thing you might want to do is subsetting. String subset, given some string vector and a pattern, will return the elements that contain matches of the pattern. It doesn't return just the matches, it returns all of the elements that contain a match. This is essentially subsetting using string detect, but it cuts out the subset operator and just spits out the whole match. If I did string subset like // parenthesis 206 on my phone numbers, it would return every 206 phone number, but the whole phone number, not just the 206s. Okay, so we're subsetting. String which will return numeric indices of elements that match the pattern. So string detect returned a big vector of trues and falses, which is what filter likes. String which will return the numeric indices. So instead of, say, getting like false, true, false, it would just return the number 2 because the second one was the one that would have been a true. Numeric indices. Sometimes you want to subset by indices instead of subsetting by trues and falses. For instance, maybe you want to run a loop, and that loop only operates on things that like meet some sort of pattern. You could say for I in string which, and it would iterate through all those numbers. It could be like 1, 7, 19, 75, and it would just run the loop on those particular ones. Complex programming stuff, but you could do it. Another thing, string replace all. So the base string replace function will do one replacement. It will replace the first thing it encounters that matches your pattern, replaces it. If you want to replace multiple things in a string, you'll do string replace all. Give it the string vector, the pattern, what you want to replace with, and it will go through and do multiple replacements within the same character, within the same element of a character vector. Okay. Okay. So from here, homework 6, part 1 is due next week. Peer reviews will be due the week after, because I've extended it a week, so you have nothing new. That's about it. You guys got any questions? It's a super short lecture. Don't want to dwell on it. Still manages to be basically dark outside. Yeah. Yes?
What's the best way to figure out regex?
Regex?
Do we just like sit down and read a tutorial or something?
Well, kind of. You know what I do, or what I like? If I go down to the, here, I've tried to get some resources for it because it is kind of hard. Let's see. This is kind of cool. This is a site that is like a what you see is what you get for regex. So you can actually type in and be like, okay. So, let's see. You see as I'm typing, it's highlighting everything that is fulfilled by that particular, like, regex. I'm getting all the spaces. Maybe I want to get something like, I want to get, say, let's go with every character. Will that do it for me? This is that'd be the best way to do that. Yeah, that'll do it. So this is me highlighting every character that occurs after a lowercase e all the way to the end of a line. By default, I'm just saying E dollar or E period asterisk. So it starts at the first lowercase e and then it highlights everything else on that line. You can kind of experiment with it. You could actually, I believe, you can fill in whatever text you want down here. And so you can just try and test it like that. That's a good way to play with it. Otherwise, there's a tremendous number of good tutorials and information if you just search for regex online. Honestly, is this the one that I like? No, that's the... This site is actually pretty awesome, regularexpressions.info. Just kind of browse around for like the quick start and the references and talks about how to use everything. The neat thing with regex is nothing unique to R in any way. Regular expressions are more or less universal, and so you can get all this regex information. Any regex information anywhere is generally going to apply in R with a couple caveats, in that you'll see that they can actually use like a single backslash in these, where in R you have to usually use a double backslash. And that's because backslash itself is a meta character in R. So you're actually backslash escaping that backslash and then using that escaped backslash to escape something else. That sounds confusing. Play with it and figure it out. I taught myself regex mostly by just messing with it and then looking things up all the time. Basically, if you have any kind of text searching problem that you can think of, someone else has already answered it on Stack Exchange or Stack Overflow or something, just look it up and figure it out. And sometimes you'll see patterns people have written. You're like, what the hell is that? Dissect it and figure it out. It's just, just got to poke at it. I never used any single resource for it. Regex are ancient, though, so there's so much resources. Any other questions?
For the homework part 2, also post one way.
Yeah, I pushed everything back a week. All homeworks have been pushed back a week. You only have 2 graded homeworks remaining, unless you hand in the extra credit one. So it's all pushed back a week. Okay, you can all get out of here. Sweet.
We have our homework part 1 due next week,
Next
and then
Tuesday.
the following one.
For part 2.
Okay,
Yeah.
I thought it was both parts to one day.
No.
Okay,
I don't gotta do that to you
okay.
guys. Jeez, you're mean. Nah, it's all pushback. No problem.
Just
Yeah.
a question. I'm conducting a research about, two different, topics, for example, safety in construction and lean construction. Each of them has, several type of, techniques, and I want to see the correlation between each of them. So I, conducted a lot of interviews around, I have around 254 pages of interviews.
Yeah.